Good afternoon, everyone. I am Pralhat from IIT Bombay. So today is we will look at much more details how molecular particle excite from ground state to some higher level of excited state. So we have this discussion started with how time dependent perturbation theory for a two state one particle in two state system. After that it gets more as the course progress. We saw how we can treat in particle systems, then how to we gone through the perturbative Hamiltonian, what is its nature, and what are the component it has, where we can see it has scalar and vector potential that is derived, that is obtained from the Coulomb-Gauss fixation of electric and magnetic field. After that, today we will look at how the what will be the probability of transition in terms of uh, in terms of the energy gap between two state, radiation energy, radiation density, and density of state. So with this, we are going to start today's lecture, which today's tutorial on solving the assignment number 4. So let's start with uh, let me share my screen. Okay. Let me share the screen. Okay. I hope my screen is visible. So let's start our lecture on assignment number 4. So this is the first question that says the your probability of transition depends on what factors. So if I look at the function p f t, then e0 square by 4 h cut square sine square wp by 2 by w square f square. So now in this formula, if I look, this wfi is nothing but energy gap between I and F. So for a particular system, this energy gap is constant between I and F. Now this omega is frequency of radiation, where delta omega is nothing but, okay. Now if I, as a whole, if I look at the function, then your this part actually contributes to intensity. Okay, this one is the modulation factor, and this is transition dipole moment integral. So this will tell about, this is actually selection rule. It will say whether this transition is allowed or not. This will tell the intensity of transition, and this is a modulation factor that actually oscillates between 0 and 1. So now if I plot this thing, uh, okay, so if I plot the modulation factor, with against the gap difference between the frequency of radiation and energy gap, what will get, we will get damping feature. Okay, so this is the line width of your absorption profile. Okay, and that is only occur at resonance conditions. So what is resonance condition? When your is 0, that means your pi is equal to W. This is also known as Bohr condition. Okay. So now if I look at the question, the correct answer should be WFI is fixed and depends upon the energy difference between initial state and final state. That is the correct option. WFI is as a function of a frequency of electromagnetic radiation. That is wrong. The time dependence of probability of finding the system in final state doesn't depend on delta omega. That is also wrong. And we know this is a this part is a modulation factor. So this is a correct option. So A and D are the correct option for the question number 1. So let's talk about the question number 2. What it says. For the system yes. Okay. So now question number 2. The for the what it says for this equation APT So now the question says, for this expression, the resonance condition, as we show here, the resonance condition only happens when the difference between radiation, frequency of radiation, and the uh, energy gap between I and F state are equal to zero. That means the um, at that point the frequency of the incident light and the energy gap is coincident with each other, and that's why you will get the maximum transition. So the resonance condition is one, the value of the transition of moment integral. Okay, the transition moment integral is says whether the transition is possible or not. If the transition is possible or is not impossible, then there is no question comes is resonant or non-resonant for the probability of transition. So this is wrong answer. Now, as I mentioned here, the resonant condition is also known as Bohr frequency condition. So this is also correct. Yes, I'm not audible. Hello, hello, hello. Am I audible now? Hello, 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 hello. I hope I am audible. I don't know. Okay. The resonance condition, this is also not correct. Still not audible? I don't know why. My mic is on. Hello. Yeah, yeah, yeah. Now can you hear me? Hello? Yeah. Okay, na? Okay. Okay. Let's start with question number three. So this is your last class, na? This this year we started late. I could not finish the probability transition admission from initial state I and final state U embedded in a density of states denoted by the correct statements is again the square of states in the United States given by conditions is independent So, so previously we take like these two transition for I to F. Now in real case, when you excite a molecule, the electronic state actually not discrete. Excited electronic state is not discrete. It's actually embedded with few number of closely packed state within a range of energy. Hello. Okay. So now, so rather uh, thinking we are exciting a molecule from I to F, we can think we are exciting a molecule. A something what you can say in more spectroscopically is kind of a wave packet. You are exciting a molecule from a density of closely packed state. Okay, so which can be written as something like that within a range of. So now the basis of considering this thing is that the transition dipole moment on exciting from I to F will not change within this energy range. And the second thing is that the changes in wave function within this E and just a little bit change of energy is negligibly small. There is actually no change in wave function. Uh, In that uh, approximation, using this approximation, this transition is valid. Okay, so as a result, you can write this equation as some constant factor into. Now we will see how we can incorporate this uh, density of number of state or density of state in the rate of absorption or transition. Okay, so now the option that are given is said that the transition dipole moment integral cannot be considered constant. That is a wrong answer. Question number B says, option number B says that number of states in the range E and E plus D is given as rho F D. Okay, that is correct. The probability of transition is time dependent. Of course, it is time dependent. Whether in the excitation is always time dependent. That's what we started with the time dependent perturbation theory. And Uh, option number D says the changes in wave function within the narrow band of energies cannot be ignored. It should be ignored, otherwise, if wave changes, maybe the dipole moment integral goes different and it may be tend to zero. Yes. Hello. Okay. So now question number 4. For the system let's look at how this expression actually comes. So then the answering this question will be the easy. So as I mentioned previously, so on excitation from I to F is not exactly on F, it's a the density of states. So what we can say that total probability of transition is nothing but the summation over so what it can be written as so what we get the finance expression is something like this. And it's x where x is uh, so we can write taking so totally we can write these things as sine square x by x cut e dx. Now if I get the derivation what we get 0 square into density state into time. So now rate of transition into Fi is depends on probability by time. So what we'll get now if I take mu square transition dipole. So what will be Then we can write WFI as 2 pi. So this is called the rate of absorption and also known as Fermi-Golden rule. Okay. So now, if I look at the formula, the question, what it says, the transition dipole is the rate of transition is actually proportional to square of transition dipole or transition dipole. So this option is not correct. Now rate of transition is dependent on density of state that we can see over here. This the number C said the above expression WFI is referred to Fermi-Golden's rule. As I say, the rate of transition increase linearly with time. As you can see, this rate of transition actually means, so this is independent of time. So rate of transition only depends on probability of transition and the density of state, and that's why and this thing actually uh, known as Fermi-Golden's rule. So this option is also correct. So now we know about the most important uh, formula uh, for elucidating the absorption spectra, that is Fermi-Golden rule. And now we will look forward around the question number 5. What is this? Now let's begin the equation of rate of transition, which is nothing but multiplication of two square matrices of transition dipole and density of state, where the transition dipole is expressed as E0 square 4H. So you can see WFI is proportional to this thing is correct. Next, transition dipole moment is solely depend on dipole moment integral, not density of state. Now, and this is actually state. This is actually the selection rule, which will say the transition is possible or not. So, based on that, we can tell the option number A is correct one. Option number B is wrong. Option number C is correct, and option number D is also okay. So, if this will take at least 5 minutes of break. We'll stay up, look after that. That will start with something called. Still now we are discussing about the absorption purpose. Now we have to look at the emission, and you know the still now it's the structure of the course says that stimulated absorption and stimulated emission, not about the spontaneous emission, which will happen eventually if you excite a molecule. So now, based on this phenomena, Einstein developed a formula that is known that will be discussed in the upcoming upcoming questions. Okay, so we'll have a 5 minute break now. We'll join after that. Let's start again. Oh, so now what we look at the phenomena after excitation. Okay, so think. So let's start. So this is suppose state one to state two, and state one has a population in one, state two has a population in two. So now if I excite some molecule with some radiation, so molecule will excite from state one to state two. Now after excitation, what will happen? So you can think the molecule was there. Now the molecule is here. Now it can. So this is come. So this is stimulated absorption or absorption, or it only says absorption. Now this is spontaneous because it will happen eventually. Now when this molecule is excited, hello, hello, yes, yes. Now when it is excited, if one sorry, sorry, sorry. Okay. Now when it molecule in excited state, now one photon if it hit and make it de-excited, it means then this is something called stimulated emission. Okay. So in thermal equilibrium, the rate of absorption will be equal to the rate of emission. So we can write thermal equilibrium, rate of absorption is equal to rate of emission. So now rate of emission can be written as spontaneous emission plus simulated emission. Now rate of absorption, if I say the rate of absorption is proportional to factor. One is number of atoms or molecules present in the state one and the radiation density. So we can write like that the rate of absorption So the constant can write E1 to 2 in one row. Now similarly can write rate of emission, stimulated emission is depend on now B2 to 1 number of particle or molecule radiation. Now, in case of spontaneous emission, it doesn't depend on the depend on the radiation. So radiation density or radiation. So it will happen eventually with the time because molecule, if you excite it for a long time, the molecule will back to the ground state. So yes. Hmm. No, no. Spontaneous emission is like if you excite a molecule and what will happen to it? So it will dissipate its energy and come to ground state. Stimulated emission it's only happen when you de-excite a molecule in terms of some excitation, some some light photon or something else. Hmm. Hmm. Energy will go with time, yes. Hmm. Okay, okay. Okay, so you are talking about is slow or fast. That uh, this comment is not so easy to see. Okay, it depends on so various factors. So now the think like the state of a molecule. Okay, so if you think the molecule in a yes, uh, see, that depends on the ground and excited state. Yes, it depends on the energy difference between ground and excited state. And we will see that if the energy gap is higher, then it will be faster. Okay, so now if you question if it dissipate its energy, where it the energy will go? That is also a question, and that actually happened. Uh, uh, that based on what is the state of a molecule. If it a gas phase or if it a solution phase. Now, yes. No, I am just extending this discussion towards the what will happen if when it emit light. Okay, emit is excitation. So what will happen if it now it de-excite? So what will happen? It can distribute its energy in other molecules which are surrounded to it. Like in solution, it can redistribute this energy, give his energy to solution molecule. Okay, solvent molecule. Now, if it in an isolated state, means gas phase, then what will happen? Now the energy will go to the various vibrational energy levels. Okay, so it depends on the nature, the state the molecule is it. Okay, so and here is you can see. what will the lecture is all only so that the energy gap will be higher, and we will see after the derivation, if the energy gap will be high, then the rate of emission will be faster. Spontaneous emission will be faster. Okay. So let's. So if you have any question, you can ask. Hmm. So spontaneous emission, it doesn't need any radiation to dxi, so it can be written as a to 1, but it needs a population. If there is no molecular particle in excitation, nothing will happen. Okay, so in thermal equilibrium we can write as B12 N1. Okay, so now if I rearrange it, what will get into V 2 to 1, wait, right again, this minus this 1 to now divide by into now. If I use Boltzmann equation with that, which now this H nu is nothing but the gap between these two states. Okay, now that what we get, and take into one common. Now, as I mentioned, the spontaneous emission and sorry, stimulated emission and an absorption in a between two same state. So you can think that the coefficient will be also same. So we can write this thing also. Okay. Now something comes from black body radiation. Now we plug this equation to the black body radiation, where radiation density is denoted as Q into now if I incorporate it, so what is the final discussion was so see if I compare one and two, this black related part it's nothing but eight. So this so spontaneous emission stimulated emission. So as you say that if the gap increases, the rate of spontaneous emission will increase. Now with this thing will be able to answer this few of question of it. So question number 6, what it says the for the rate of transition. So rate of absorption depends on two factor. One is population of first state one and radiation density. So option number one is correct. Rate of emission depends on N1 and N2, not N1, only N2. So this is correct option. Now option number C says the rate of spontaneous emission depends on radiation density. That is not correct. Yes. And rate of simulated emission depends on yes, simulated emission depends on both the factors. So now question number 7. So this first question is coming from Blackboard. So see the calculation now. How to look at this? The row radiation is written as A2 to 1 into. Now in denominator B1 to 2. Now B1 to 2 if is there, then this should be N1, and 2 to 1 it should be N2. So this is wrong answer. So this should be in mind while choosing the answers. And second thing, when so the accurate expression is exact expression is A2 to 1, then B1 to 2 N1, 2 to 1 N2. Now if I divide by N2, we will and then we will get and we incorporate the N1 in N2 as Boltzmann's function, we will get the equation C. And similarly, as we can write B1 as B2 as B, so option number D is also correct. Now question number 8, for a molecule AB whose dipole moment is along Z axis and directing with also from line. So the from Fermi-Golden rule, what we can write squares square of modulus of square transition dipole moment can be written as E0 if I take E0 inside an arrow. Now this is all about the now in for up to this point we are considering light is isotropic in nature. Then you can think on all the direction x y z. Then it has one third contribution in every direction. So now what is saying the molecule is aligned along to yes. Huh? Hello. Hel- Hello. One by three times of mu z square. Yeah, we will come to it. So if the molecule is aligned to the z axis, then what we can see that so one third contribution will go to the z axis and on that basis we can write whatever you are saying along the z axis. So you are correct. So what we will get or we can write like this. So okay. So option number B, sorry, square. B and C are correct. Question number 9. For the system number D. Now there is a way to bypass this question. I have some shortcut, but we'll go through the uh, proper way of looking at. Uh, so transition dipole is written as 1 by or huh? Okay. In rate of transition or you can insert. So everything has two different kind of expression. Now for monochromatic and discrete transition. So here to here. So now there is the density of state can be written as only the radiation density. So where we can write to T nu or so okay, we have to integrate it. Otherwise, it will not get result. So, so the main point of this question was isotropic and non-monochromatic for question number 8. But here they are asking about a discrete transition. So the- just by looking the question, you can omit all these three options. So the question, as you say, the red new will be the correct option. So this kind of maybe similar question will not come in the exam, but who knows? It may come. On the last question for uh, the again visiting to the Einstein equation. So what it says, the ratio and A and B is nothing but ratio O of rate constant of simulated emission and spontaneous emission. So A is for spontaneous emission and B is for simulated emission. So the option is wrong. P is ratio of A and B directly proportional to the energy gap between ground and yes. Hello. Hmm. Yeah. Then then the what is the question? Says the option number C says hello. Actually, directly not directly proportional. You cannot say it. It is actually cube term, na? Okay. Yeah. So the Einstein. Okay. So moving to option last two options. Einstein's coefficient A and B are directly proportional to square modulus of transition dipole moment. Okay. So it is very easy to say because B is nothing but your rate of absorption, that is we can see proportional to square modulus of transition dipole moment. As B is proportional, then A is also proportional. So the option is correct. And now D, what is the for large E, delta E values, A is greater than B, that is correct, which means spontaneous emission dominates over the simultaneous emission. That is a correct option. Okay, with this, we have covered all the questions of question number 4. So I think this is our last class. So I will upload all this thing in the portal, and as I have not covered all these things because due to we started late because we were instructed that we came to know about this class later. So what we will do, I will do upload the previous year uh, assignments assignments what we covered last year. So who are interested, you can go through it, and uh, that lectures is also uploaded in YouTube, and you can see whatever is left in the last year uploaded video. Okay. Yes. Yes. Hello. Okay. 21st. Yes. Yes. 21st October. September. Okay. 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 Question will be no, there will be no descriptive question. Everything will be this option marks for MCQ or MSQ. So it will be as similar as the assignment. So the thing is that please note the correct starting point of derivation, so that you can just by looking at the formula, uh, some expression will be given in the questions. Okay, so by using some trick you will be able to solve it, being like that, because remembering all the derivation is not so easy task. Okay, and I will upload this previous year's questions answers, how to solve it or not, and you can look at the videos. Okay, so I am stopping it here. All the best for your exam. Okay.